name is Alexander Jarman. I run the public programs here. And it's been a wonderful summer so far. We've been able to work with so many great, wonderful artists, including tonight. And before I introduce Dr. Geoffrey West, I just want to say a little bit about tonight. We asked the question at the Summer Salon Series this year, what does a city need? Tonight we're focusing on design and planning. So we've got a fantastic installation piece in the lower rotunda, which is a map of all the swimming pools in Del Cerro that you can then build upon. We just had a fantastic performance piece where the artist designed the score, but then really couldn't plan on how the performance was going to go because the computers that were feeding the notes to the musicians were all generated randomly. So it was a great, wonderful surprise. But to cap it all off tonight, we have what I sort of consider our keynote address of the summer by Dr. Geoffrey West. And we've really got to get this lecture started, so I will be very brief. But I read about Dr. Geoffrey West in the New York Times Magazine a long time ago, and I felt like I met him once I had read that article, and I knew that there was going to have to be some way that we got him to the museum this summer. He just got back from, is it Scotland? It was he just spoke at the TED Global Conference in Scotland, and I would encourage you to go to TED and look up his talk there. But tonight he's here live in the flesh, and he's going to tell us all about how cities work. He is a distinguished professor at the Santa Fe Institute, and it is my great honor to have with us tonight Dr. Geoffrey West.
Thank you. Well, thank you, Alexander, for that very nice introduction. And it's a real pleasure to be here. And it's so wonderful to be able to talk, first of all, to such a large audience in such a wonderful room. And indeed, of course, a room like this, in a place like this, is a real hallmark of what cities in many ways are about. That is, you know, when men and women started talking to one another, interacting and forming communities 10,000, 15,000 years ago, this is what it's led to, and it's kind of wonderful. And the kind of underlying theme of this talk is actually whether any of this is sustainable. This is great, and it's been having you know, a profound effect upon the planet. And I would say that the greatest effect that human beings have had on this planet has all happened in the last couple of 100 years, and it's happened through the exponential rate at which we have urbanized. Urbanization has been kind of the crucible of civilization. It has led to all the wealth creation, the kind of quality and standard of living that everybody, certainly in this room, takes part in, benefits from, contributes to. But it's also led to an enormous threat. And the enormous threat is not actually to the planet, and in fact, I don't think it's even to the biosphere, it's actually to ourselves. And that's really what the underlying theme is of the talk. And you can see it's kind of this long, kind of 18th century title to the talk that has a kind of story. Let's see if this works. Whoops, no, wrong one, this one. Yes, so there it is. So the question is all of this sustainable? And I think an even bigger theme that kind of even overshadows that, really, in order to answer it, is, are there kind of laws that we can discover where we can put it in, and I should have said, and it wasn't said in the introduction, I'm a physicist, so I look at this through a physicist's eyes, which is that in order to understand, we need to put things into a quantitative, analyzable framework in order to be seriously predictive, and that means to some extent to what can we mathematize? what we're talking about. And I'll develop this as we go along. So I've already said a little bit about urbanization and the phenomenon that something extraordinary has been happening in the last couple of 100 years, and we only have to look at ourselves in the United States, and I've written down just some statistics there, that over the last 200 years we've gone from being a few percent urbanized, most of us being in really agricultural environments, to the opposite, namely that I think it's something like 82% of Americans now live in cities, and a small minority is actually agricultural. In fact, it's only of the order of hundreds of thousands relative to the 350 million of us that populate the United States. And a few years ago, the planet crossed this halfway mark, and if we continue on the trajectory we're continuing, by 2050, the planet will be pretty much urbanized, at least 75%, it may be much higher, and we will have gone from almost 7 billion people on the planet now to close to 10 billion people on the planet. And just to give you another sense of it, in the next 25 to 30 years, in this time frame, China will be building of the order of 300, maybe even more, cities, new cities, each in excess of 1 million people. Now, this is going to have a profound effect on all of us. I mean, those that remain alive in the next 25 to 30 years will be affected by those cities being built in China because they require an enormous number of resources. So that's just one small piece of the problem. And I've written down a statistic here that if you average over the next 30, 40 years, that a million people a week are being urbanized. So this is kind of an extraordinary phenomenon that's happening, and I want to talk a little bit about some of its consequences. And I've written up there, urbanization, the problem, because all of the problems that we face today in society, this kind of tsunami of problems, I mean, the most recent, of course, is the last few days, the behavior of the markets, economies, the questions of global warming, the environment, health, pollution, disease, crime. All of these are basically urban problems. They all originate in the cities, and they are all propagated from the cities through the population. On the other hand, the great thing about cities is what I started this talk about, is all of this. This is what's happened by us becoming urbanized and interacting with each other, forming all these marvelous phenomena, culminating in works of art and music and culture and great restaurants and all the rest of it. But most importantly, that's happened because cities have been like vacuum cleaners or magnets, sucking up creativity and wealth. Creativity and innovation, and creating wealth and culture. So the problems that we face, this extraordinary tsunami of problems that we face, which originate in cities, are going to be solved by cities. And the real thesis of this talk is that since cities is where all the action is, the good, the bad, and the ugly, we better really understand the dynamics, growth, and organization of cities in a predictive framework. So that's going to be what I'm going to be talking about. Incidentally, one of the other aspects of this that we have to recognize is that all of those problems, from the financial markets all through the spectrum to global warming, which seem to have come upon us in the last 5, 10, 15 years, of course have been with us for the last 200 years, even longer. All those things have been happening. The reason that we feel them now is not because they're new, it's because of this exponential growth. They've been happening exponentially in the same way that I talked about, going from a few percent to 80%. All those problems have gone from being a few percent 200 years ago to less than 50% 100 years ago, to being totally dominant now and happening faster and faster. So that's our problem. Okay, so next. That 10 billion people, most of whom will be urban, want this. They want what you see around you here. All those people on the planet want that, and they want it to come from things like this, to be supplied by things like this, and have things like this. It's what everybody wants. I don't care where they're from, some version of this, maybe, okay? Some version of this and this, okay? What most of us don't realize is that, or haven't realized, is that if you want all of this, coming along with it has to be, at some level, I'm sorry, driven, I left out a sentence, all of this stuff, of course, driven by this ever-increasing economy, the market's always going up, but as a result of that, not only do you get all that wonderful stuff from this growth, but you get this, 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 and this. It's inevitable. This comes along with it, and for anyone here that's had a physics course, this is called entropy, and it is an inevitable result of all the other stuff. The whole question is, can we control all the bad and still have the good? Otherwise, is that what San Diego is going to look like in 50 years, rather than, or every other city look like that, rather than that, or that, or that? That is you, in fact. But is, okay, so that's what you'd like, is it to remain like that, rather than being basically a slum with a few very wealthy people. Okay. So, as I said, we need a serious science of cities, and I think to understand the whole thing in a bigger sense, we need something I whimsically coined a kind of grand unified theory of sustainability, which includes all of these problems, and I will come back to this at the end. And so again, as a physicist, I ask, are there kind of underlying universal laws that are governing all these phenomena that we can somehow put to use in addressing these issues? And what I'm going to talk about tonight is work that I've been involved in for the last few years, but it's actually only scratching the surface of the problem. But it's really an attempt to come to terms with some of these big issues. So this was the framework inside of my head, so to speak, that I wanted to start thinking about this problem, and it was driven a lot by work I'd been involved in the past. And that is, the first question was, are cities and companies just very large organisms? And that came about because we use metaphorically organismic biological terms often to describe cities and companies. We talk about the DNA of the company, the metabolism of the city, the ecology of the marketplace, and so on. These terms are often used metaphorically, and the question is, are they just metaphors, or is there some serious substance to it? So is San Diego a great big elephant, and is Microsoft a great big anthill? Or to what extent are they? Or is that just total bullshit, and we should just not even think of metaphors like that? If such metaphors have any content, there is a secondary question that I had become interested in, and that is this astonishing phenomenon that cities, despite appearances, are extraordinarily resilient. It's very, very difficult to kill a city. Almost no cities have ever vanished. You can think, of course, of classic examples that you're familiar with, and you can think of ghost towns, but of the hundreds of thousands, millions of cities, communities that have evolved on the planet, almost all of them are still with us, whereas on the other hand, of the millions of companies that have been formed on this planet, all of them die. So one of the questions is, what is the ongoing trajectory of a city like San Diego? And on the other side of things, when is Google going to die? And can we predict these things? Because it will. All these companies die. There are many of you that are my age and know I'm an immigrant to the United States, and when I first came to this country, you know, I learned this marvelous thing: what's good for GM is good for the United States, because GM was, you know, the most powerful company, and it was inconceivable that GM would ever die, which it did, as you know, 2 or 3 years ago. Now there's some new thing called GM, which was resurrected because of the government. Okay, we'll come back to that at the very end. Okay, so these are just some of the characteristics that you're familiar with life in general, and of course you can use all of them as metaphors, as I already said, for cities and companies. And as I said just a few minutes ago, whoops, this is the framework that I like to work in. Incidentally, if I don't use the microphone and I come out here, which I much prefer to do, because then I'm kind of with you rather than behind this silly podium. Can you all hear me? I have a fairly loud voice, but if not, I'll use the microphone, which I can walk around with, but I'd rather not. Can you hear me at the back? Yes. Tell me if I start to wane later on, just tell me to speak up or to use the microphone, but I prefer to do it this way. Okay, let's try it and see how it works. So, this is the framework. I already said this. This is the framework I want to try to develop. So the way of thinking is, I want to start talking about things like this first, ecosystems. And this is what is in my head for talking about it. That's what I want to do, and I want to somehow get it across to you. Okay, but I want to do it for cities as well as for ecosystems. So one of the first questions is, to what extent, if any, is this just another version of this? Okay? Well, one of the reasons for asking that question is that despite the fact that when you walk through a forest, it looks like a random collection of big trees and small trees and, you know, just looks like kind of a random mess, beautiful mess, but kind of, it doesn't seem to have structure. Despite that appearance, this has extraordinary structure and extraordinary regularity. So that, for example, if you ask any question you can think of about any quantity associated with that picture that is conceivably measurable, such as how many trees are there of this size, how far do I have to walk from this tree to find a tree of similar size, what is the, so to speak, the distribution or density of trees of a given size, how much energy is flowing through this branch, how many leaves are on this branch, how tall is this tree, etc. Anything you can think of about the organization, structure, even the growth of mortality of this forest, you can answer and put into a mathematical framework, and it tells you that there's this thing, though looking random, has unbelievable structure when put into a mathematical framework. So I can answer all those questions about the size and distribution of trees, of branches on those trees, leaves on those trees, how much energy and resources they're using, how long individual trees might live on the average, how many trees are being born, etc. So the question is, so you have to believe me when I say that can be done, can we do the same kind of analysis of, whoops, I want to go backwards to that, okay? So I'll show you 1 or 2 pictures about the forest a little bit later. And the way into trying to come to terms with either a system like this or like this is a phenomenon called scalability. And I just want to spend just a few minutes talking about it because it permeates a lot of the discussion. So here's what I mean by scalability, for example. This is us. Namely, we are one of these. We are a mammal. That is the smallest mammal, a shrew. This is a shrew that sits on the palm of my hand. This is a shrew on the scale of an elephant, which you're familiar with. That's not so surprising. This is an elephant on the scale of the biggest mammal, the blue whale. In fact, of course, the biggest organism that's ever existed on this planet. And it still blows my mind, actually, that this great big elephant actually is tiny on the scale of a whale. And the thing that I want to get across is that these are all representations of the same physics and chemistry, organization, dynamics, called mammals, and they persist over a range of what we say 8 orders of magnitude, meaning that the whale is 100 million times bigger than the shrew, but it works in pretty much the same way. Now, this kind of phenomenon that you have different representation of the same underlying structure and dynamics, even though superficially they look different, and I'm going to emphasize that in a moment, actually permeates the whole structure of biology and social life. And the reason for this is that if we are to be resilient and robust, meaning that we want to have organisms and life that continues over not just tens and hundreds of years, but millions, billions of years. Life has been going for several billion years, and the only way it can do it is if the phenomena can scale in the same way over many different sizes. So, for example, just to emphasize the point, this little cartoon up here is something called the Respiratory Complex, which is the little engine. It's a bunch of complex molecules that sit inside your cells and produce something called ATP. It's a chemical, but that ATP is your energy, actually. That's how all of us in this room are staying alive. In fact, it's what most of animal life relies on. It's this fundamental object of what we call respiration, bringing oxygen in, oxidizing food, and giving you energy. Well, there are up to 1,000 of these little engines inside a thing called a mitochondrion, which is this potato-looking thing. So there's about up to 1,000 of these inside this, and there's up to 1,000 of these inside a cell. So there's about 1 million of these little engines inside each one of your cell. Now, 1,000 of these things can't act incoherently. They have to act all together in some beautifully integrated way so that this mitochondrion can function in a robust way, and then up to 1,000 of these mitochondria have to act in a beautiful, integrated, holistic way so that this cell can function, and then 10 to the 14th, 10 raised to the 14th power, lots of zeros after that 1, 14 of them. That's how many cells are in your body. All have to act in some beautifully, again, holistic, integrated way so that I can stand up here and talk to you, and you can either listen or doze, but you can go on living, and you can go on living for 100 years. Not only that, you can do this as you grow in the beginning of your life. So all this has to act in some beautiful integrated way so that you can function, or you here can function, and then you can come together like this, or in groups, again, in a beautiful, integrated, holistic way, and make things like this, or if you had turned out to be a thing like this, make things like this, and then make things like this with cities and businesses. So all of this, which I showed earlier, is actually just a manifestation of what these chemicals are doing. That's what food goes in, is acted on by this, and it goes through an extraordinary process and produces things like this. It's fantastic. But it can only happen, and it can only persist for hundreds, thousands, millions, billions of years if there are what we call emergent laws which constrain the way these things can interact. Okay? So that's kind of the idea, without giving you any mathematics and so on. And I'm now going to show you some things about that. And one of the things I'm going to talk about in this talk is growth. And one of the things you know about growth is that you start growing quickly and then you stop. Okay? I mean, you stop, I mean, you may get fatter and so on, but you basically stop growing. You understand what I mean? And this, whoops, I want to go back. I have this one. So here it is, you grow and then you stop. This is you. This happens to be you as a rat, but we're all pretty much the same. I could have shown you, for us, it would look very similar. This is great for us, and the fact that we have stopped growing and you spend most of your life in this very stable state, and that you do not, as an individual, evolve. We as a species may evolve, but as an individual, you are you for your entire life. It's great for biology, and it is one of the reasons that it is so robust. This is true of almost all of life, and why it has been on this planet for 2 to 3 billion years. This is in marked contrast to this, which is social life. We do not want in social life things that look like this. What we want are things that look like this. Here it is here, there's the same graph, but for companies. This happens to be revenues of companies versus their age. I should have said this, I really apologize. This is, just to make sure everybody's on the same page, the weight of a rat versus its age. That's what we call a growth curve. Here's the same phenomenon for a company, but except this is revenues versus age. And you can, but these are a bunch of software companies, and they all look like hockey sticks. They're all zooming away. And that's our image of the economy. That's the image of companies. And that's the images that we see projected up here. So this is quite different, this image, and the paradigm that we have evolved, certainly in the last 200 or 300 years, with our capitalistic free market system, which has been so extraordinarily successful. So there it is. So I've shown this one a moment ago. Now, the other side of it, of course, of life is death. And we all go through that. And as I say, companies go through it, but cities don't. And I will talk about that in a moment. There's some examples. We've mentioned them already. But the way into this, as I say, is scalability. And I want to now make this a little more precise. And I'm doing it by showing you a graph here, which is that of the most fundamental quantity, really, in biology. In fact, it's the most fundamental quantity, really, of a city or of a company. It may be called something different, but in biology it's called metabolic rate. So here it is in watts. That's how much energy you need per second to stay alive, sitting there doing what you're doing now. What is shown in this graph is that metabolic rate, energy per second, plotted against, on this horizontal axis, the mass, the weight. And what you see, and it's plotted in a curious way, but it's a way so that you can get all these animals on it, is plotted in this way where instead of linear, is plotted in something we call logarithmic, but all it means is that you notice this is 1, 10, 100, 1,000. It goes up by factors of 10, as does the weight, 1 kilogram, 10 kilograms, 1,000 kilograms, all the way up, so that you can get an elephant and a mouse on the same graph. And what you see, if you plot it this way, is something extraordinary. So let me back off a second. Each one of these animals, each organ, each cell type, each gene has evolved in its own unique environmental niche with its own history over hundreds of millions of years. So each one is unique, it looks unique. So you would have expected, had you plotted a graph like this, that these would be all over the place, just representing somehow the accidental things that happened in the evolution of, say, the goat versus the evolution of the giant rat. Okay, and they do indeed look different. Yet, when you plot metabolic rate versus their size, you see they all line up on a straight line in this way of plotting them, indicating that despite natural selection and the randomness in natural selection, that there has been some extraordinary constraint that means that if an organism evolves to be this size of a pig, its metabolic rate, despite the fact that metabolism is the most complex and physical process probably in the universe, despite that, its value is determined despite the complexity and the history and the environmental contingencies. So that's pretty extraordinary. What is kind of interesting is that the slope of this line, the gradient, is approximately 3/4, and that 3/4 is less than 1. Let me explain to you why that's important. What you might have expected, maybe, at the most naive level, is the metabolic rate would go linear. That is, if you double the size of an organism, so you double the number of cells, you'd expect you to double the amount of energy to stay alive, which would mean, and I should have drawn it on here, instead of a line like this, the line would have gone up here, like that. That would be a linear. But the slope is 3/4 means it's less than linear. We call that sublinear. And that means that instead of when you double the size, you need double the energy, you actually only need 75% roughly more energy. So there is what we call an economy of scale. The bigger you are, the less energy you require to support the same gram or pound of tissue. Your tissue is pretty much the same as a mouse, but you actually require less energy to support all those cells than a mouse does, but your horse does even better. So the bigger you are, the less energy you need per gram to stay alive. That's what this graph says in a systematic, apparently law-like way. Okay. Now, it turns out if you plot in this way any physiological variable you can think of, so this happened to be metabolic rate, but you could plot heart rate or the rate of diffusion of oxygen across some membrane, or any life history event, like how long do these things live? How long do they take to grow? Whatever you can think of, you plot them this way, they all look like this, they all line up like this, and I may have shown you some. That's just showing you that this law, so to speak, is true across all of biology. That's what this graph shows. I'm going to go quicker now because I've spent too much time on it. It is also true down at the bacterial cellular level. This line, this line here, this line is actually the same line that is going through all the mammals, going through you and me and the elephants and the mice. But it's down at the cellular level. So there's some extraordinary, what we call universality that's going on that is somehow making something that is the most diverse and complex phenomenon in the universe behave in some simple way, represented by these graphs. So I've said this, and that stuff in red is that it, as I said a moment ago, this kind of phenomenon, this scaling phenomenon propagates across and transcends across all of biology. And it basically says the following. First, if you give me the size of an animal, I can tell you, at roughly speaking, the 90% level, almost everything about it. I can tell you almost everything about its physiology, how fast its heart beats, how long it will live, what is its metabolic rate, how oxygen diffuses across its lungs, the size of its aorta, you name it, I can tell you for the average hippopotamus everything about it. Put slightly differently, it says that although the whale lives in the ocean and the elephant has a trunk and the giraffe a long neck and you and I walk on 2 feet and a mouse scurries around, in fact, we are all scaled versions of one another following these kinds of laws that I've indicated here. Okay? And that the elephant's trunk, our walking on 2 feet, and that little mouse, all of that stuff is only the superficial, in quotes, 5 to 10%. That the majority of it is somehow constrained by these laws. And what I'm going to talk about in a minute is where in the hell does that come from? What is it that is forcing this constraint? Okay, let's see what's next. I just showed some more. I'm not going to spend time. I'm just going to flash through. This happens to be heart rate versus weight, your body mass. You see, it decreases systematically. The bigger you are, systematically, the heart beats slower. And it happens to be a law that says, for example, if you increase by a factor of 10,000, 4 orders of magnitude, the size of the organism, the heart beats 10 times slower, 1 to 4 in that sense. And it turns out lifespan, there's a lot of fluctuations in this, increases as mass to the 1/4. That's down here. You see this is a fit. They're very close to 0.25. And what is interesting about this is actually a slight digression, that this said heart rate decreases in a certain way. Turns out lifespan increases in exactly the same way, such that if you multiply them together, you discover that, what I've said here, that the number of heartbeats in a lifespan is pretty much the same whether you're a whale, a horse, or a shrew. So what you get from this is that the little things live life in the fast lane. Everything goes extraordinarily fast. Heart rate of a shrew is more than 1,000 times per minute. The heart rate of a whale is kind of once every approximately a minute, I think. So that's an extraordinary range. So you have to wait a long time between those booms, whereas a shrew is boom, 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 boom. But if you add up all those beats, it's basically the same over the whole lifespan. Okay? So if you understood that number, you would understand why I can make a prediction, a serious prediction. Everybody in this room will be dead in 100 years. In fact, looking around me, it may be I could say, oh, everybody in this room, many of this room will be dead within 20 years, for example. Why is that? Why isn't that number 1,000 years or 1,000,000 years? I might say a few words about that later. So there's just some other ones. I'm just showing you data. That happens to be white matter to gray matter in the brain. It's extraordinary. This is the brain, unbelievably complex, yet something just impressionistically you get something simple is going on. That's gene size and so on. And underlying all of this, and this is the main point of this, is the mathematics of networks. Because a critical part of all of life, both social and biological, is the role of networks. The obvious ones that you're familiar with are your circulatory system. It's a big network that delivers blood. Your respiratory system, your lungs, your renal system, your bones are a network, your brain is a network, and all these networks are interacting with each other, but they are all governed by mathematical principles. And it turns out the mathematical principles of those networks, which are universal in their mathematics, if you put them into a mathematical framework, can explain all of the laws that I showed you in the last 5 to 10 minutes. So I just show you pictures of these. You're familiar with them. That happens to be the circulatory system feeding the brain, but that's the brain itself. That's the white to gray matter. And you can see there are all these network systems. Oh, that's a little thing I don't know what, I forgot its name, lives in an elephant. I forget its name. That's inside a cell. There are networks inside cells, and you can use that structure. The structure of the network explains all of those phenomena, including plants, the way plants work, trees work, and indeed, when I showed you that picture of the forest, that in fact is a network. Those trees are actually networked because even though they're not connected by tubes, they are networked because they have to allocate and apportion energy between them. The energy coming from the sun, the water, the root system that goes down to the earth and so on. So obviously this is not the kind of lecture where I can show you any of the mathematics. You have to kind of believe me that there is such a framework that has been done, the calculations carried out, and all of those things have led to the understanding of those laws. And I just show you one example because it was done by an undergraduate actually that worked with me for a number of years. He's now just finishing up as a graduate student at MIT. And it was taking that theory of the forest and asking the question, can we predict the height of the largest tree if I know how much rain falls and how much sun is shining and what is the local temperature and so on? So this is a map, and I honestly do not remember which is which. One of these maps is the theory map, comes out of the theory, and the other is the data. And you can see there's differences, but you can also see that there is a very good agreement between, let's say, I think this might be the theory, and this is the data. And you can look at this, those that are experts in it, you can look at statistical analyses and convince yourself that this gives a very good fit. Okay, so we think we understand a lot of these things, and one of the applications of this whole framework is going back to this question of growth, and this, and the same theory that gives rise to all those scaling laws and predicts the height of the biggest tree, predicts that line. That comes out of the theory. That line giving the growth of a rat or of you starting very fast, and it explains why it stops growing and how big you will get. And the theory is extremely simple in its conceptual framework, and this has to be put into mathematics. It's very simple. You eat, you metabolize that food to make this ATP, and what do you do with it? You maintain all the cells that are there, you replace cells that have died, and you make new cells. And you have to put that into mathematics. And if you do that, you predict that line, which gives, and those dots there are the data. Okay. And that's a whole bunch of other data for other things, and I'm going to skip this. The only reason I show this is it's a similar thing, and I'm not going to explain this other than to say this has also been done by other people to predict the growth of insect communities. So now we're moving towards the cities. This is communities of insects. This is ants and bees and so on. And there it is. And it's even been done to predict the growth, just finished, just paper just coming out in about 2 weeks, the growth of cancer, how cancer grows, understanding how cancer grows, and why it is that it's bad to have a cancer growing inside you, but it's good, apparently, to have babies growing inside you. That doesn't seem to cause, I mean, and that's an interesting question. Why is one good? Why does one kill you? And in most cases, it doesn't kill you. It comes out to be very good. So you have to understand that. Oh, and that's just showing you, I'm not going to spend time on it. So here's the summary of this whole part, this first part, just to remind you. Biology is dominated by something we call power law scaling. Those straight lines, that's just a technical phrase. And there's this funny number 1/4 that keeps occurring, which the theory explains in a very elegant way. Not important for this, but it is important that the scaling, first of all, that it scales non-linearly, and that it scales, what I said, sublinearly. The slope was less than 1, which gave rise to this phenomenon of economies of scale. The bigger you are, the less you need per capita. Something I didn't emphasize, very important, is the bigger you are, the slower you are, the slower the pace of life, meaning things diffuse slower, things flow slower, you live longer, but in a systematic, predictable way. That gives rise to the fact that, as I said earlier, the elephant is moving very slowly, and the mouse lives in the fast lane. One lives a long time, one dies earlier. Growth is what we call sigmoidal. That's the technical word for growing fast and stopping. And underlying all of this, it is claimed as the mathematics of networks. And so the question is, can we take any of this stuff over into cities and companies, which of course are also networked? Oh, these are some of the people that I've worked with. I just throw up their names. I can talk about them maybe a little bit later. I want to, actually. And these are people that I've worked with on cities, and they're an interesting bunch. And the first question that we asked is, are cities scaled versions of one another? I mean, after all, it is a bit weird to think that an elephant is actually just a blown-up mouse. It is. That's what. If you ask, what would an elephant look like if it only weighed, 20 grams, it would be a mouse. That's what a small elephant is, or a small human being. We're a cat, actually, in these terms, to a large degree. Okay, so is San Diego a scaled-up Boise, which is a scaled-up Santa Fe? They look very different. Their history, geography, cultures are actually quite different. But are they, in fact, scaled versions of one another in the same way the animals are? And is there some universal behavior to any of this? Okay, next. Well, as I said, the theory before was based on networks, but it's very obvious that cities, and companies for that matter, as I said, are networks. That looks like a network. They're supplied by networks. But the most important thing about cities and companies is not actually the stuff we think of when we think of cities, this and so on. I could show you lots of such pictures, but it's this, you. This is a social network. People, cities are manifestations of the networks of people. Okay, and I'm going to emphasize that later. That is, this, you can't see this, but this is just people interacting with each other. And it is the way we interact and our clustering, our family structure, our job structure, our governance structure. These all have network phenomena, and it is the behavior of that network which determines actually a great deal about cities and companies, because, just to repeat it again, despite appearances of all these wonderful buildings and roads and slums and so on, they actually are representations of us through our networks. Okay, so here's the answer to the question. First of all, the first work I got involved in with some German colleagues was plotting gas stations. It's called petrol, which was a European petrol stations. Plotting that in the same way we did the biology. There it is on this, going up by factors of 10 here. Number of petrol stations, number of gas stations versus the size of the city using population as the metric for size. And what did we discover? Whoops. What did we discover? But that they do scale. There it is. Okay. I mean, there's fluctuations, of course, and I will come to that. And on this graph, we did plot in linear. That would be linear, meaning double the size of a city, you would have double the number of gas stations. That's what that line would represent, or this line. But you see its slope, like in biology, it scales, and it scales with a slope less than 1. There is an economy of scale, not surprising. The bigger the city, you expect to have less gas stations per capita. Not surprising. The thing that's surprising is that it seems to follow approximately a very regular rule. And it's the same rule no matter where you are. France, Germany, Spain, Netherlands, we've done it all over the world. It's pretty much the same. The slope of this It's not like the biology, which was 3/4, 0.75. This is more like 0.85. And I will come back to this. So that was surprising. There seems to be a universality of gas stations. But it turned out, when we looked at anything associated with infrastructure, the total length of roads, total length of all the electrical lines, water lines, whatever you wanted to think of to do with infrastructure, they scaled like this. But more importantly, they had the same slope. So if you double the size of a city, you have an economy of scale in gas stations, an economy of scale in roads, an economy of scale in electricity, and so on, all to the same degree. They're all integrated. These are integrated systems, and so there is a crucial interrelationship between all of the infrastructure. In a sense, not surprising. The city has to function. It goes back to what I was saying before, scalability. You need to have this integrated. But there it is in the data. But what really surprised us was when we looked at quantities that have no analog in biology. Roads and electrical lines are very analogous to the kinds of things that we were talking about earlier in biology. But things like wages, or things like AIDS cases, or things like patents have no analog in biology. They are phenomena that come about and only came about when human beings started forming communities, talking to one another and acting together in a communal sense, and recognizing that working together we can produce the same thing for less energy per capita, or for the same amount of energy produce more per capita. Okay? And one of the things we discovered in the data is represented here. This is the wages as a function of population for, this happens to be American cities, and this is a plot of something called super creatives, people like you lot, as a function of population. And what you see again, there's again these fluctuations, but there is a generic trend, this red line, and this red line, this is just a fit to the data. Beta is just the Greek letter for the analog to the slope of this line. And what you see, it's pretty much the same for both of these quantities, but more importantly, it's bigger than 1. It's not less than 1. And now we have a different effect. That is, the bigger the city for socioeconomic quantities like wages and super creative people, you get more per capita. Okay? So San Diego will systematically have more creative people and have higher wages systematically than Boise, for example. Or Merced, I'm trying to think of California cities, I don't know. And what we discovered was that this is universal. First of all, in the sense that it applies to all socioeconomic quantities. There's patents. Has the same, I forgot to write it on here, has the same gradient, the same slope as these, about 1.15. It's the number of patents produced. But it's also not only across different socioeconomic quantities, police protection, tax, construction, debt, crime, but it doesn't matter where you are in the world. It happens to be crime in Japan. You could plot on this crime in the United States. The overall scale will be different, but the way individual cities relate to one another is the same in Japan as it is in the United States, as it is in Portugal, as it is in Bogota. It's the same. And what we did, just to show you here, plotted on the same graph are income, GDP of the city, crime, and patents, which are superficially not related. And you can see there is some spread in the data, but the general trend is they all go together in an integrated way. Okay, so here's the statement. If you double the size of a city, whether from 50,000 to 100,000, 5 million to 10 million or 10 million to 20 million, doesn't matter. If you double the size, you will get systematically, on the average, a 15% increase in wages, number of patents, number of fancy restaurants, but also number of AIDS cases, amount of violent crime, etc., etc. All of these socioeconomic quantities come together to roughly a 15% every time you double, and at the same time, you have a 15% savings on all infrastructure, roads, electricity, and so on. So cities, the bigger the city, the better everything is, except for the problem of crime and pollution and disease. So it's in a certain sense no wonder that cities continue to keep growing in this sense, because they're extraordinarily attractive. People are willing to ignore and feel they can shield themselves from crime, pollution, and disease because they can get all these good things. And these good things all come about by the multiplicative enhancement of social interaction represented by the network effect of people coming together and forming communities and working in this kind of integrated way, which I will explore again in a moment. So I'm sorry, this is a bad slide. It's a messy slide. I'm not going to read this. This is a quote from Goethe about the pace of life in the early 19th century. But I just want to say one thing about this, and that is that in biology, we had this economy of scale. Just to repeat, economy of scale gave rise to sigmoidal growth. You stopped growing, and the pace of life slowed as you got bigger, and this was all related to networks, and the networks giving rise to these exponents, this 3/4 and etc., which were less than 1. What we see in socioeconomic life is that these exponents are bigger than 1 by about 0.15. They're bigger than 1. Instead of getting less per capita, these quantities are more per capita. More AIDS per capita, more patents per capita, more wages per capita, etc. If you look at the social network that is driving this interaction of human beings and the way we cluster, as I said earlier, then this says we have as a prediction of that instead of the pace of life slowing systematically, the pace of life has to increase systematically, and it's governed by this 1.15. This 0.15 governs the pace at which life gets faster and faster, and it comes about from this continuous multiplicative behavior of interaction coming through the network structures that we create. And most importantly to recognize about this is the following. Not only do we have this systematic scaling, but I emphasized earlier, it's universal, not only in the quantities, in the variables, in the characteristics that we look at, from AIDS to patent production, but it's the same across the globe, independent of geography, history, and culture. Just to repeat myself. How in the hell can this be? Japanese cities knew nothing about European cities or American cities in their evolution. These cities evolved essentially independently, yet they're all behaving in this systemic, universal way. What is underlying it is the universality of human interaction, of social networks. So independent of culture, these networks pretty much have the same structure. So for example, just to give you one example, the network that we are most familiar with is the one that is immediately around us, which I will call family. It needn't be family. That is, universally, a human being can only, I would use this word, love in a serious way, have a powerful interaction with maybe 4 or 5 people. Okay? You can have 500 best friends on, not YouTube, what is it? Facebook, or one of those things which I hate. Well, I must say, just parenthetically, I am wholeheartedly a 20th century person. I'm not a 21st century, and it's good. I'm 70 years old, and I'm going to drop dead within the next few years, no doubt. And in that sense, I'm pleased, because I hate all that stuff. Okay, that's personal rant. But seriously, no matter where you are on this planet, no matter which culture you're in, there is only a very small number of people that you have very strong, powerful interactions with. Even if you come with a family of 15, you only really interact in this deep way with 4 or 5 people, maybe your parents, 1 or 2 brothers, or if you're children, and so on. That's a universal kind of number, and there are numbers like this throughout the network that are independent of culture, and they are being reflected in these scaling laws. Okay, so here's the pace of life. On your left is heart rate, modern data, and there's this kind of funny 1/4 for the slope, but the important thing is it's decreasing. Heart rate, as I said earlier, it's decreasing with size. Bigger you are, the slower the heart rate. Here on the right is a whimsical quantity in socioeconomic life, is the rate at which you walk, walking speed, and what you see plotted in this way, there's quite some variance. There's obviously a systematic trend that you walk faster in bigger cities. This happens to be European cities. There's sort of mixed data for American cities. And the slope of this is a little lower than the prediction, but it's pretty good. It's kind of amazing. And of course, walking is also a social phenomenon. It's part of the network. You interact subliminally, at least, as you walk. But we have lots of other data showing the rate of social life. This is an aside comment. One of the unintended benefits of cities, big cities, is, I said all those good things, there's another good thing, they're greener. And this is a plot of the carbon dioxide emissions as a function of city size. And here you see it scales. This is 2 different phenomena, but it doesn't matter. They're both representing carbon. And what you see, look up here, this number is the slope, the gradient of this, and this number is the slope of this, and they're both less than 1. That means, in English, the bigger the city, systematically, per capita, less carbon is produced. Very, very good to have big cities despite the appearance. Of course, overall you're producing more carbon because you have to add everybody up, but per capita, better to be in San Diego than Boise. Better for the United States and the planet that this city gets bigger and bigger from this viewpoint. Actually, from almost every viewpoint. Very good to have big cities. That's why there are megacities. One of the reasons there are megacities continue to grow. So it's all those people living in these idyllic little communities, rural communities, that are the people causing much bigger problem. It's true. For carbon. It's true, actually. Okay. This is not original with us. This is, okay. So the other thing I want to emphasize from this data is that since everything scales together, what it tells you is something I kind of alluded to at the beginning. All these problems that we're concerned with, from markets to the environment and global warming, should not be thought of as independent. They all scale together. They're all created, I said, by the cities, but then I explained to you that cities are you. Cities are this network of interactions that all of us participate in. And all of these phenomena are to do with us interacting, and it is a network that underlies all this, and it is this network of social interactions, which means that all of these are actually manifestations of the same thing. So solving global warming without thinking about disease or thinking about the financial markets or thinking about congestion is problematic. It's a classic problem that we have in something called complex systems. and in fact complex adaptive systems, because these systems are continually adapting, like cities continue to adapt, is that if you only treat one piece of it, and you forget about the rest, you have enormous numbers of unintended consequences. You could turn that around also and say that one other characteristic of such systems is that one piece of it, even a small piece, can have enormous effects on the whole unless you think of it in a systemic way, so that a very tiny effect in the mortgage industry has had these enormous consequences, has brought down the economy of several countries, and may yet have extraordinary effects, which we're still suffering from on the economy of our country. So this is a lesson that unless we have an integrated, holistic, complex systems view of all these phenomena, and we go on treating them as individual pieces in a kind of stovepipe way, I think the lesson is that we're doomed, that we can't do it that way, and I want to explain why that is so. I think in the next, I'm going to leave this out, in the next. Oh, I wanted to summarize here. This was just the first, just to summarize what I said. We have this greater than one behavior, which we call superlinear behavior. The bigger you are, the more you have. We have the increase of pace of life. And now I'm going to talk about the last thing here, the question of growth. Oh, yeah, I'm going to miss this out because I've gone on too long, and I was going to talk about cities, but I want to talk about growth. I'll come, if there's a question, yes, he's telling me to go fast because I've been, as usual, talking too much. So we talked about this earlier. This was biology. This sigmoidal growth, you grow and then you stop. And that comes about because you have sublinear behavior. If you have superlinear behavior, you discover through the equations that the problem that you see in this for economies and cities, that you stop growing, which is considered bad in our modern paradigm, that's considered bad, whether you find beautifully consistently that if you have what I call superlinear behavior, bigger than one, the same framework tells you that you can continue to grow like this. That's what this is. But it actually has a big catch in it, this theory. It says, actually, you can't go on doing this. And it is actually related to the fact that eventually you run out of a resource, whatever it is. It could be coal, iron, electricity, whatever. But at various times, what you do is you discover some major new resource, and that sets a paradigm for the society, like coal, giving rise to steam in the Industrial Revolution. We discover oil, we invent computers, we move on to IT. Each one of these is kind of a revolutionary change, a paradigm, and that is represented by this, namely that these equations tell you that you grow, but that eventually if you do not change, if you do not innovate, you will, go to this, you will collapse, that's what it says. If you innovate, you make a major change so that effectively you start over again, this is what happens. So you grow, you would collapse. It's like running out of resources. So you make a major innovation and you grow again in the same way, and you can continue to do that. So there's kind of a theorem that if you want to continue to grow, that you must continue to make major innovations. Well, that's what we've done. We've done it brilliantly. And this theory is a very nice mathematical representation of that, and there's lots of data to support that. But there's a huge catch, an enormous catch. First, I have to remind you that as time goes along here and you grow, the pace of life gets faster. It's the first thing. You're going to get faster and faster. Everything gets faster. But what this also says is that not only does the pace of life get faster, but the time to go from this innovation to this one necessarily is, and systematically has to be shorter than the time to this, which is shorter than this. Namely, that the time between innovations systematically has to get shorter and shorter. So put slightly differently, it says that this thing here is not the clock that determines time. That's some external thing. Our socioeconomic time, which is actually governed by the network of interactions, is actually going faster systematically, faster and faster, necessarily. And so it is as if we're on this treadmill that's going faster and faster. It's accelerating. And the question, the fundamental question is, can you go faster and faster without having a heart attack and falling off? Because what this says is that something that may have taken 100 years, 500 years ago to do, or 1,000 years, 10,000 years ago to do, only takes 25 years to do now. And in the future, that will only take 18 years. And then it's going to take 12 years. And then you're going to have to make, I mean, to take this to a kind of reductio ad absurdum, you're going to have to making a major revolution in terms of innovation every year, every 6 months. Well, on a local scale, we feel that. We were talking earlier about the computer, but I don't have it here. But, you know, I could pull out my iPhone, and you know, every year or two, this bloody thing changes. And unless you're 22 years or younger, you can't keep up with any of that stuff. There's already, at a kind of psychological level, for many of us old farts, this problem that we're seeing the tip of the iceberg. And so this brings up a huge question as to whether this whole thing is sustainable if we insist on this kind of behavior, which is what has evolved, particularly in the last 200 years, that the growth paradigm is it. Okay, I just have some data. I'm going to finish up here. This is just data. The last thing, the last two things, do I have a few more minutes? Where's he? He's run out. Oh, he left. No, can I take just a few more minutes? Yes, okay. So here's one thing. I didn't point out on that graph of metabolic rate, some of you with keen eyes might have looked across at the axes. You notice it was watts on the vertical axis. And if you looked across at a man and a woman, you saw that you only use 100 watts. You sitting here, staying alive, is a light bulb. That's all. Stay alive. It's phenomenal. You are unbelievably efficient. Turning off a light bulb, sound like my mother, could feed a person in the Sudan, literally, okay? It's amazing. We're only 100 watts. Now, that's what we were as biologically. Actually, it's 200 watts or so, because if you add it, you have to add in what I'm doing, energy and so on. So you add in all the energy you use to do your work, a hunter-gatherer, and there are still people on this planet whose metabolic rate, active metabolic rate, is about 250 watts. They're hunter-gatherers. And all of us, 10,000 years ago, used about 250 watts. Now you can ask, how much energy you use now? What is your social metabolic rate? That's what that number is, 11,000 watts, and that's who you are. 30,000 kilograms. So you can turn this around and say, how big an animal do you have to be stupid enough to be using 11,000 watts? 30,000 kilograms. And 10 billion people on this planet want to be like you and me. They want all these things. I mean, in their own cultural form, of course, but all of them want it. This is nuts. This is not possible, nor ultimately does it appear to be sustainable. We need to make a change. Or, of course, this is an interacting adaptive system, it will make changes. And those changes may be beyond our control in terms of governance. You know, they will lead to all kinds of social unrest. So there's a huge problem, and it desperately needs a big integrated view. Okay, I want to finish up very quickly. I'm not going to do this. This is not my work, but this is just showing the speed at which things happen. I'm not going to spend time on it. I'm just going to finish with one thing, and that is talk about companies very briefly, because you can ask the same thing. Do companies scale? Is Walmart some blown-up version of some diddly company in downtown San Diego? The answer is yes. Here's data. This is assets and income for a bunch of companies, and there's some fluctuations at the beginning, which I don't have time to talk about, but you can see it's pretty good scaling. There is scaling, and we've learned that the slope plays a crucial role in this, and especially if it's bigger or greater than 1. What is amazing about companies is they're less than 1. The number is here, is about 0.8 or so. That is, they're dominated by economies of scale, which means that instead of looking like that, which is what we want, the hockey stick, if they're economies of scale like you and me, what does that say? That says you stop growing, which is terrible for a company, apparently, and they die, like you and me, okay? So here's what looks like a counterexample. I showed you earlier some. I showed you pictures of those hockey sticks. Here's Walmart. Wonderful, zooming away. But actually I only got up to 94 on this. If you go to 2008, that red line is from the theory. So it's kind of inspired by the theory. So if I was smart, if I were really smart, I could have done this in 1985 and predicted where Walmart would be in 2009. That's what that graph says. But it means it's curling over. And you say, well, okay, what about the rest of the companies? There they all are. That's 22,000 publicly traded companies in the United States. And you can see, here's all the newborn ones, hockey sticks. You see, these are sales. You can see sales, not big sales, but they're all zooming and so on. But look what happens when they get to, I forget how many dollars, what that is, how many billions of dollars. They're all flat. And they're all going to die. Good riddance, I say. And here's the graph, the last graph I'm going to show. This is a mortality curve, and what this shows is the probability of dying here. 1 would be you're dead versus the age, and you can see that once you're beyond about 30 or 40 years, all companies die. And of course, there's some outliers that live for 100, 200. Even there are a few companies that are 300 or 400 years old. Those are mostly breweries and wineries and a very special niche. So this is just a little impressionistic thing, and I think I'd better finish there because I've gone on too long, because I suffer terribly from ADD, so I like to go off in all kinds of... So I'll stop there, but I just want to leave you with the lesson that despite what looks like uniqueness, whether you think that San Diego is unique, and there's a whole piece of this talk I left out about how you extract the uniqueness. But, you know, at the 85, 90% level, you tell me the population of San Diego, I can tell you approximately it should have, you know, 473 police, 212 AIDS cases this year. The length of all the roads is whatever it is, you know, 5 million kilometers, I don't know, some number. This amount of construction, et cetera, et cetera. And it'll be approximately right. And I missed out a piece that shows that. So there are these laws that on the average, in what we call coarse-grained, and that underlying them is what we've been doing tonight. Talking and interacting with one another, loving each other at the very local level, and having some kind of interaction, which may be, albeit weak, across the whole structure. So that I love my wife and my children, and I have some sort of bizarre very long-range interaction with the president and all those other idiots that are in Washington causing us trouble. And I will finish on that note. Thank you very much. So, thank you. Thank you.